Okay. Okay, let's get started. Okay. You see, we actually have like a class of over 80 students, but now like yeah, this classroom is still too big, right? Yeah. Yeah, but it's okay. I mean, as I say, like I don't take attendance. Okay, so and we record the sessions. In case if you want to study at home, that's totally fine. But of course, like coming to class also has the benefit. I mean, if you have any question, you can ask me directly. Okay, so. Last week, okay, we talked about a basic concept about Bayesian inference. Basically, like is to use the evidence to change your belief. Okay, so of course, last week we only vaguely talked about this concept. Okay, but I mean, it's obviously, you know, very intuitive, right? But we need to pin down this mushy concept, okay, into like a mathematical form, okay? And to do that, of course, we need to have a little bit of mathematics, but not too much. And all this mathematics that we talked about today, I mean, you should have learned that from your high school anyway, okay? I mean, you learn high school like a probability, right? Like those stuff like a long time ago. So I suppose like you shouldn't have problem with that, okay? So that's, okay. As I said, okay, the Bayesian inference is, I mean, putting this in a simple term, is to reallocation of credibility across possibilities. Okay, so for example, on a typical day at your location, okay, what is the probability that it is clouded? Okay, it's cloudy. I mean, for example, like today, I think it's cloudy, right? So I think in here, okay, in Zhongli, okay, we probably have like a, you know, higher than 0.5 chance, I mean, to have cloudy days, okay? I mean, this is actually better than my hometown, okay? I grew up in Keelung, okay, which is known to be like a raining city, right? So, like when I was like a kid, okay, Keelung was terrible. You probably go through like weeks, and every day it's raining. Okay, every day for like I mean, like week long, or even like more than a couple of weeks. So Keelung is much terrible, but I think Taoyuan is probably close to 0.5. Okay, so suppose you are told it's raining. Now, what is the probability that it is clouded? I mean, if it's raining, most likely, okay, maybe more than 90%, it is clouded. Without a cloud, there's no raining, right? So pretty much like, you know, the probability of cloudy it should be much lower than the probability of cloudy on the condition of raining. You guys know this notation, right? This is a conditional probability, right? Okay, so of course there's the reason I say like it's 0.9 or 90% is because there are still some occasions like you see like you have rain, but it's sunny day, so it's I don't know the English term for that, like, but you guys get the idea. I mean, in Chinese it's called like what's that? What's the Chinese term for that? I don't remember that either. But anyway, like sometimes when it's sunny, you still have rain. Okay, but that's not very likely. Okay, it's a very, rare occasion anyway. Okay, so this is exactly what we are looking for, right? That's reallocation of probability across possibilities. Okay, so suppose instead you are told that everyone outside is wearing sunglasses. Then, it's not very likely you see people wearing sunglasses like in a cloudy day, right? I mean, unless that guy is blind, right? I mean, but let's see, the chance you bump into blind people, okay, is not very high anyway, right? So again, okay, the probability of cloudy should be much larger than the probability of cloudy on the condition that you see like everyone outside is wearing sunglasses. Again, this is a conditional probability. So you can see that, okay, another example of Bayesian inference. And you can see when you put down those things into like a probability, then you know like this has connection to the conditional probability. Okay, so Bayes' rule, okay, which you should have learned that from high school probability, but probably you don't feel it's like that important, okay, when you learn that, okay, in high school, okay, but it is an important mathematical tool, okay. It's merely the mathematical relation between the prior location of credibility and the posterior location of credibility conditional on data. So here, okay, let me explain. The P clouded is the situation you without any data, right? When you don't have any input, okay, the probability of clouded is your prior, and then you receive some data. Okay, for example, in this situation, maybe you see like it's raining, or you see like a situation like people outside they are wearing sunglasses. Okay, so these are the input you receive. Okay, or you can say they are data that you observe. Okay, and once you have this data, okay, that will change your probability, right? So this like a conditional probability, okay, either in the first case or in the second case, are what we call posterior. Okay, posterior. Okay, so you can see that, okay, the prior allocation of credibility, which is this one, and the posterior reallocation of credibility, okay, is this one. Okay, they are different because of the data, right? So that's exactly what we are talking about, the Bayesian inference. So so we need to bring you guys back to some basics of statistics, okay? Because probability and the statistics are kind of like intertwined together anyway. Okay, so what is statistics? Okay, basically it's the collecting, organizing, analyzing, and interpreting data. As I said, remember I told you last week, like the Department of Statistics, they consider themselves like the Department of Data Science. Okay, this is rightfully so. Okay, because you can see statistics is to dealing with data. Okay, anyway, so there are two main statistical methods. Okay, that are used in data analysis. The first one is what called exploratory data analysis, EDA. So normally, okay, it's this is the tool that help us to do certain summary of the data. Okay, for example, like a mean, mode, standard deviation, the interquartile ranges. Okay, so all this. Okay, when you are given a set of data, you can compute and obtain some number out of this data. And obviously, they are a summary of this set of data. Okay, so EDA is also about visually inspecting the data using the tools you may be already familiar with. Okay, for example, histograms, and scatter plots. I mean, because after all, I'm not, checking high school textbook for quite a long time. But I'm pretty sure, like in high school textbook, you probably learn histograms, scatter plots, and from the high school, right? Okay. 长条图啦那些 okay. So this is like the first type of statistical method that you can use for data analysis. Okay. The second type of data analysis is about making statements beyond the current data, which is called inferential statistics. Okay. So for example, okay, we may want to understand a particular phenomenon. Okay, maybe we want to make predictions. Okay, for future. Okay, or need to choose among several competing explanations for certain observation. Okay, so the inferential statistics, okay, is the set of the tool, okay, that you will learn in this class. Okay, they are, of course, like a traditional inferential statistics and the Bayesian one. Okay, and we, of course, in this class we are focusing on the Bayesian inference. Okay. And the statistic approach, okay, is a better approach because, okay, it's ontological, okay, and it's technical, okay. So actually, to be honest, like you probably cannot say like deep learning is statistical approach, but because it's complicated, okay, too complicated. But you can rightly say like machine learning methods, a lot of machine learning methods, okay. If you try to look at them, okay, from a statistics point of view, okay, they are kind of very similar, okay, and so statistics actually is like a mathematical framework that can be used, okay, for all these different inferential methods that you have learned from machine learning, actually. Okay, so this is like a very powerful tool, statistics. Okay, and also it's technical. Okay, in the sense that there are some model software tools. Okay, such as PyMC3. Okay, so we can utilize these tools to define and to solve the model, okay, very easily, okay. So of course, I mean, this chapter we are still not going to talk about PyMC3 in detail, but we will talk about that, I mean, very quickly, okay. So you don't, okay, in the past, without this tool, okay, it requires a very high level of mathematical, understanding, okay, or I mean, or even like it's near impossible to do certain inference based on the data. But nowadays, okay, because of the availability of these tools, and obviously because of the computer, we are able to do that. Okay, I think hopefully I'll talk about that today. Okay, why I mean computer and the software becomes so important in Bayesian inference. Okay, so after we talk about the method, okay, of course we need to also talk about the data. Okay, so data is I mean, the most important ingredient in statistics and data science, obviously. Okay, and we know that data actually come from many different sources. Okay, for example, you can collect data from experiments. Okay, or you can get data from the computer simulations, or you can do some surveys to collect data, or field observations. Okay, some data, okay, may be collected very inexpensively. Okay, for example, if you are doing surveys, okay, a lot of time doing surveys very normally inexpensive. Okay, but computer simulations, okay, well, as long as your simulation tool is not so huge, okay, the current computer like speed, okay, normally okay allows you to collect a large amount of data, okay, inexpensively, okay. However, okay, there are a lot of experiments, okay, or field observations that can be very expensive, okay, because some physical or chemical experiments, okay, it requires a lot of like investment to do even one experiment, okay, and if you tell like a lot of time like we people, I mean in computer science, okay, when we are doing inference, we are really not those people who collect the data. Okay, I mean a lot of time when you are, analyzing the data, you actually only obtain the data from somebody else, okay, who already, did some experiments or to collect those data for you, okay, but really like a lot of like this data collection process, it could be very expensive, okay, or field observations. Think about that. I mean, some data may be like, for example, medical data. Okay, you want to see like a lot of like a rare disease data set. Okay, but the rare disease, because it's real. I mean, it's rare disease because you don't get to see so many patients with that symptom, right? So if you want to collect a lot of data on that rare disease, that's also very challenging. Okay, so there's a whole branch of statistics, okay, to talk about how to do data collection, okay, this is known to be experimental design, okay. But yeah, we are not going to talk about this field, okay, because as I said, okay, in this class, we assume, okay, we already have the data, okay. We are not, going to talk about how do we, make sure the data collection is done correctly. This part is not, but if you are interested, there are other, literature you can check out, okay, in the experimental design. But and also this is an example to tell you like some experiment could be very expensive. For example, Large Hadron Collider, LHC. Do you know this thing? 就是那个粒子碰撞器 okay, in Chinese, okay. This thing, okay, I mean, it's this facility actually takes years to construct, and each time you do this experiment, okay, of course you can receive like hundreds of terabytes data, but well, this experiment equipment is just very, very expensive, okay. I mean, like there are only a few this type of facility, and each facility is the size of pretty much a city, okay. And to operate these experiments, okay, you need like thousands of engineers, okay, to do that. So this is like so complicated, and obviously the data is also so expensive, okay. And this is important, okay. You need to understand, okay, even though we, as I said, we are not going to deal with data collection, but you need to understand as a general rule, okay, the data collection, okay, the process of generating the data as stochastic. What is stochastic? Stochastic is probabilistic, okay? If you don't know this term, okay, it is pretty much similar to probabilistic, okay? So because there's ontological, technical, or epistemic uncertainty, okay? So for example, when you collect the data, okay, sometimes you cannot take into account of all the factors that, affect the data collection. Okay, you cannot, I mean, even with a very, very controlled experiment, there are still certain factors that you cannot fully control. Okay, and also like a lot of time, like when you measure the result, okay, you collect, okay, from the experiment, okay, the measurement itself is also not so accurate, okay. After all, it's, I mean, it is not, generated from computer. I mean, for computer simulations, yes, you may be able to get a much more accurate measurement. But yeah, I mean, in computer simulation, it is simplified model. Okay, when you simulate certain events anyway, so it is again, okay, not so accurate. So the system is intrinsically stochastic. Okay, so there are technical issues. Okay, that will add noise or restrict us from measuring with arbitrary precision. Okay, and there are conceptual limitations. Okay, I mean, for data collection. Okay, so because of that, okay, we consider data to be stochastic. Okay, there are uncertainties. Okay, for data, even though we are not dealing with data collection, but even though we are given the data, you need to understand data is stochastic. Data are stochastic. Okay, we always need to interpret data in the context of models. Okay, including mental and the formal ones. Okay, so data does not speak but through models. And some of you may have questions like, okay, so I mean, in this class we are talking about models. So what exactly are models? Okay, models normally means a specific, assumption. Okay, and that assumption comes with some parameters. Okay, let me use we are going to talk about that. I mean, quickly. I mean, for example, like standard deviation. Okay, standard deviation has some parameters, right? Its mean is standard. The normal distribution. Normal distribution has some parameters. Okay, for example, the mean and the standard deviation, right? So basically, like then normal distribution with mean and standard deviation can be considered as a model. Okay, so anything that comes with certain parameter that you can adjust, it's a model. Okay? So in this class, we assume we already have the data that are already collected for us. Okay? And our data will also be clean and tidy. Okay? Something really true in real world. Okay? Actually, I mean, because I'm doing some projects. Okay, even for data you obtain from the government. Okay, there are missing values. Okay, there are missing values, and a lot of missing values that you adopt that, like those government employees. I mean, are they doing their job, or they are just drinking coffee every day? So I mean, it's really a lot of time you feel like the quality of some data, I mean, offered by the government is really unacceptable. Okay, I'm talking about I don't know if you guys are familiar with this website. It's called 民生公共物联网. Okay, 民生公共物联网. You can do a search of this term. Okay, and this is I believe it's a government run data portal that allows you to download, for example, like a PM 2.5 readings of different area. Okay, and for example, like water resources, and a lot of open data. Okay, but you will find that the data offered by the government, the quality is so lame. Okay, so as I said, okay, in the real world, okay, the data is never clean, never tidy. Okay, but anyway, okay, in this class, let's not worry about that. Okay, let's not worry about data collection. Let's not worry about data cleansing. Okay, data cleansing by itself is also important research. Okay, including like data imputation, including getting rid of the outliers of the data. Okay, but let's assume the data that we have at hand are already good. Okay. And also we need to talk about sample space. So what is sample space? I mean, because after all, we are talking about statistics, right? So the sample space is a set of possible outcomes. This will map into this. Remember, I told you possibilities are outcomes, right? A set of outcomes, right? So normally this possibility, okay, a closed possibility, these possibilities, okay, is, it can be considered as our sample space. Okay, so for example, when you flip a coin, okay, the sample space is head and tail. Okay, I know some people, when they flip the coin stands, right, on the edge. Okay, that's a very rare case. That's not consider that very rare case anyway. Okay, so when you flip a coin, you can only get like a head or a tail. Okay, and if you throw a dice, okay, there are 6 possible outcomes, right? 1 to 6. Okay, so basically, okay, so if the coin is fair, when the probability of coming up heads, okay, will be 0.5. Okay, we normally denote, okay, the probability of a certain event as theta. Okay, but okay, this theta is already a probability of coming up head. Okay, but we consider this probability of coming up heads is 0.5. This whole sentence, okay, as a theta. So degree of belief about a parameter is denoted as P of theta. Okay, so this is you may wonder what's the difference between this one and what's the difference between theta and the P theta? The theta is referred to the probability of coming up heads for a coin. You can say it's a parameter. Okay, you can say it's a parameter. Okay, and degree of belief is how much you believe this probability is true. Okay, so for example, we might believe that, okay, the coin is fair. Okay, when I say the coin is fair, I mean theta equals to 0.5, right? The probability of this is 0.99. Okay, if the coin was minted by the federal government, well, because you get this coin directly from the government, and there's no particular reason to consider this coin is, there's any problem. When you flip this coin, okay, 没有被做手脚 okay, so you can say, okay, you pretty much believe, okay, this coin is fair. Okay, or put it another way, okay, how much do you believe your government? Okay, some people think, okay, I trust my government only up to 90%. Some people think, okay, I trust my government to 99%. Some people say, okay, I I love my country, okay? I consider the coin is fair. If I get this coin directly from government, I will treat it as fair coin. I will consider it 0.999, okay? Very, very, very positive. Okay, so this is like a belief. It could be different, okay, from person to person, okay, because it's a belief, okay. So both probability of head or tail outcome and the degree of belief in biases refer to sample spaces, okay. And but these two things are different, okay, in statistics, because probability of head in coin flips, this thing is outside the head. What do we mean? Okay, it means it can be sampled. Okay, I mean, if sample, this word is not familiar with you. I mean, familiar to you. I mean, you can say this type of thing can be experimented. Okay, you can flip this coin any number of times, and you can see if this coin is fair. Okay. So this is like something you could do. But the belief, okay, when I say I believe this coin is fair, okay, I have, or put it another way, like okay, this where is it? Okay, P of theta equal to 0.5 is 0.99. Okay, this belief, okay, is inside the head, so it cannot be sampled, because even different people may have different belief, right? So because it's inside the head, so how can you sample it, right? Okay. However, the mathematical properties of probabilities are the same in their essentials. Okay. Here I just want to tell you, okay, the first type of understanding to probability is exactly what I told you last week, the frequentist understanding of probability. Okay, the event can be sampled, and based on the result of the samples, large amount of samples, you get the probability distribution. Okay, but some events cannot be sampled. Remember I told you like an election example. Okay, here, okay, we are talking about another example. They just cannot be sampled. It's more like a belief. Okay, it's more like a belief. Okay, here, okay, the reason we talk about this is because we are talking about relocation credibility, right? So this credibility, if you remember in last week lecture, we talked about credibility is equivalent to probability, and I told you belief. Okay, belief is also referring to probability. So these three terms, okay, belief, credibility, probabilities, are pretty much the same in this class. Okay, so here we talk about this because I just want you guys to understand this credibility concept. So, for example, as I said, like you can approximate the probability that a coin flips. Okay, the probability that the coin, like a flipping coin, come up with head. Okay, by doing a lot of experiments. Okay, you can approximate that probability. Okay, but even if you do that, even if we take frequentist approach? Well, even for a fair coin, okay, it seems so obvious that we should get about 50% heads in any long sequence of flips. But if you try to really flip the coin, okay, you will see that this is the probability, of the head, okay, with the number of flips. Obviously, when the flip number is small, okay, the probability can be, can fluctuate a lot. Okay, but even if you flip like 200 times or even 500 times, you see, okay, even if this coin is very, very fair, to be honest, we get this not through the real experiment. We get it through computer simulation. So we can really set the generation of the head or tail to be pure random, okay, just 0.5, okay, because it's computer generated. But even with that, you can see that, okay, it's not exactly 0.5, right? The proportion of heads is just near 0.5, but not necessarily exactly equal to 0.5. Even with a very long sequence of the experiment. Of course, here we are doing computer simulations, but you get the idea, okay? So there's a limitation for this frequentist, approach. Okay, this is another limitation. Okay, because you can never get like the exact 0.5, the proportion of heads is never exactly 0.5. Okay, just very difficult to get that. So of course, okay, if we know this this coin is fair, okay, we can derive the probability directly, okay, because sample space of the coin will be head and tail, okay. So by the assumption of fairness, so we know that each outcome is equally likely, and we know like a probability, okay, for head and tail together should be 1, right? Because that consists of the whole sample space. Okay, so so the long run relative frequency of heads should be exactly 0.5. But this is not done by the experiment. This is done by derivation. Okay, and this idea, the derivation can be extended to other simple situations. For example, like a fair dice. Okay, for fair dice, like each side have a 1/6 probability to come out. Okay, to come up. I mean, you can the derivation is pretty much the same. Okay. So let's come back to talk about this belief, because belief is subjective. I mean, well, as I said, like different people, different person has different belief. So obviously, belief is subjective, right? So how strongly do you believe that a coin minted by the U.S. government is fair? I mean, as I said, like different people have different belief in their government. I'm pretty sure like the people who voted for Donald Trump will have different belief, like to their government, right? Than those who voted for Joe Biden, right? I mean, yeah, let's not use like Taiwan politics as an example too much. Okay, using U.S. as an example probably is much more fair. Okay, much more like political correctness. Okay. So how about a coin purchased at a magic shop? Obviously, if you see somebody come out from a magic shop with a coin, you probably don't believe that coin is fair, right? Okay. So to specify our subjective belief, we have to specify how likely we think each possible outcome is. Okay. So, but this is, as I say, it's a mushy intuitive belief. Okay. So how do we pin down this intuitive, mushy intuitive belief? Okay. This pin down process basically is calibration. Okay, we want to calibrate the subjective beliefs. Okay, and the interesting thing, well, yeah. So the interesting thing is that we can, for example, okay. Let's use an example. Okay, how strongly do you believe that there will be a snowstorm that closes the interstate highways near Indianapolis next New Year Day? Because you guys are, we are in Taiwan, right? So we don't have snow, okay? I mean, even if we are we experience like a very cold weather, like some people even drive like a long way to the mountain to see snow. But in U.S., okay, this is like a lot of area in U.S. like snow is really a terrible thing. Okay, this some of these slides, by the way, I mean, first I want to tell you some of these slides, because I remember I told you I used to use the book Do Bayesian Data Analysis, okay, as a textbook. So some of those slides actually are still from the previous from the courses that I used to use that textbook. So some of for example, this slide is from that textbook, and it happens that the author of that textbook is a professor at the Indiana University. Okay, Indiana University, Bloomington. And if you don't know, I got my master from that school. Okay, so I stayed in Indiana for 2 years. Okay, so I have a very close connection to Indianapolis. Okay, Indianapolis is the biggest city in Indiana. Okay, which is about like 15 minutes drive, 15 minutes away from Bloomington. Okay, IU Bloomington. Okay, so anyway, okay, I can, from my own experience, I can tell you that New Year Day. Okay, every New Year Day, like the interstate highway near Indianapolis, okay, it's very likely to have snow. But in north part of U.S., even when they have snow, they will put the salt on the road, okay, to make sure the snow will melt. Okay, so a lot of time, even when it is snow, okay, the interstate highway will still be operating, okay, still be operational, okay. The chance for the highway to be closed, okay, it is only when two occasions. The first occasion is when the snow is really heavy, okay, it's really heavy. It's too heavy that the salt cannot melt the snow fast enough. Okay, it's possible. Okay, it's possible. And the second possibility is that, okay, when there's a freezing rain. You may say, well, if it's rain, then why do you need to be afraid of the rain? But it is the freezing rain is more terrible than the snow, okay? Because it is supposed to be rain, but because the ground temperature is too low, when the rain come near the ground, okay, it is frozen into ice. Okay, so when there's a freezing rain, okay, a lot of time the road will suddenly become very, very slippery. Okay, very, very slippery. So it's very dangerous. It's very dangerous. Okay, and because it become ice. I mean, even before it arrived the road. So the salt doesn't work so well with for the icing rain. Okay, so this is a second occasion, like the interstate highway will be closed. Okay, so but anyway, okay, if you ask me, I would say that I will have a good share of belief. Okay, next New Year Day, okay, the interstate highway near Indianapolis will be closed. For example, like probability for that maybe 50%, 0.5. Okay. So, but the issue is, this is a belief, right? As I said, as we just discussed, we need to calibrate this belief, right? Okay. So, so how do we calibrate this belief? Like, because I have a strong belief, but how strong is it? Previously, I told you 50%. Okay, but a lot of time when you think of this, even if you don't understand, okay, if you don't know about Indianapolis, you may have a certain belief, right? But if I ask you, what's your probability? You probably cannot tell me, right? You cannot tell me your probability. I mean, for this belief, right? So, okay, you can try to do this experiment. In the sack, we put 10 marbles, 5 red and 5 white. We shake the sack and then draw a marble at random. The probability of getting a red marble, obviously, is 0.5, right? This is high school, well, to be honest, like high school, like probability class. I mean, everybody knows that. I mean, this is probably the simplest question that you can get from high school anyway. Okay, so now let's consider this. Set 1. Okay, gamble. Okay, because we in Taiwan people like gamble, right? Okay, actually like this is a human nature. Okay, so everybody like gamble. I probably should say that. Okay, so gamble A is you get $100.